Root finding is a hard problem, and there are many methods to solve it, a lot of which we've discussed on this channel, such as Turon-Kerner, Alberth-Ehrlich, Stephen's method, Jenkins-Straub, and even Lehmer-Schur. The difficulty with these methods is that they may have issues of multiplicity or finding complex roots. You may also need to give them really good starting points, and sometimes they may not converge, if they're even stable. That's why I usually recommend Lehmer-Schur, except that algorithm can sometimes chase squirrels, may not account for multiplicity, and has lots of overlapping tests. It works by drawing circles and using a circle test to determine if a root is inside of that circle, and then uses repeated rings of circles to test for more points, until eventually converging on an answer, oftentimes the smallest root, but that's not necessarily guaranteed. Instead, Wilf uses rectangles to avoid a lot of overlapping tests. Let's assume the rectangle test works and start with the search. Here you can see our method determining if a root is inside of a square. It even counts for multiplicity, telling you exactly how many roots are inside that square. It stops once the squares have gotten small enough. Wilf's original paper has him starting with a square of random side length and then growing it until the test tells you how many roots there are that match degree. A better approach, just take the coefficients of a polynomial and use the Cauchy bound, using this formula to come up with a radius, and all of the roots will be contained in a circle of that radius. Use that for your starting square. As an example, let's look at x cubed minus 1. Our radius would be 2, drawing this circle, and if I overlaid it with the roots, our method's able to find them all. The thing about the test is that it won't include the borders, so we're actually going to alter the starting point to avoid the real number line. In Wilf's paper, he uses a random point inside the unit square, and then retry if for whatever reason it doesn't work. I recommend just making a small shift, and then if it doesn't work, use a retry. Then keep searching with 4 squares, and stop once your squares become small enough and you found all of your roots. We've discussed the search, now let's tackle the rectangle test. But first, a simplified example and a special function called v. This is the polynomial of x squared minus x minus 1. We're going to test 4 points and evaluate them with v, giving us results of 2, 1, 1, and 0. There's a neat equation that says v of a minus v of b is the number of roots, such as v of minus 1 minus v of 0 lets us know there is 1 root, minus 1 to 2 lets us know that there are 2 roots, 0 to 1 says no root in this interval, and 1 to 2 says there is 1 root. Note though that this number for roots includes multiplicity and doesn't actually include a and b. It's using what's known as a Sturm sequence, only finding real roots for now. A Sturm sequence starts with your polynomial as f0, using the derivative of the polynomial to be f1, and then using synthetic division to come up with a negative remainder of the last 2 functions in our series for f. We'll stop once we have a non-zero constant, and if you ever do hit 0, factor out the repeated root first using the greatest common divisor, and then restart the process. In our example, f of 0 is x squared minus x minus 1, f1 would be 2x minus 1, its derivative, and then f2 is 5/4, our remainder after division, giving us these signs. Our v function is the number of sign changes in our Sturm sequence. These are the actual values if you want to plug them in. There's also a sign function, not to be confused with the sine function, giving you back values of 1, 0, and minus 1 for positive, 0, and negative values. Looking something like this. Before we go further, we need to talk about Fourier. Fourier's approach started with f0 being the polynomial, f1 being the derivative, but rather than using remainders, The next set of f's were all the successive derivatives, all the way down to whatever degree you had. Then you looked at the sign changes skipping zeros and used this equation, the same one from earlier, of v minus a minus vb to give us our number of roots. This was a generalization of Descartes' rule of signs, also codified in the Fourier theorem. The one drawback for this is that the roots that it gives you is only an upper bound on the number of real roots. Going back to our earlier problem, let's just use Fourier's approach and see what its results are for our v functions, and they are exactly the same. It still works, but each of these numbers is only an upper bound. Sturm's approach gives us an exact number of real roots. Sturm thought to use division instead of just derivatives, and it worked. He was trying to investigate Descartes' rule of sign and extended Fourier's upper bound theorem, giving the famous Sturm polynomial that we know today. He also worked with Fourier as his assistant while they were in Paris. Charles Hermite once said that Sturm's theorem had the good fortune of immediately becoming a classic and of finding a place in teaching that it will hold forever. His demonstration, which utilizes only the most elementary considerations, is a rare example of simplicity and elegance. Strangely, although the theorem quickly became a classic, it was soon relegated to history and, contrary to what Hermite believed, vanished from the textbooks. That is, until mathematicians realized it could be used to actually solve for complex roots. Here's how Wilf did it. First, he used a rectangle in a complex plane, and this equation to tell us the number of roots inside that rectangle. It involves pi and arguments, it's a little tricky. Then, by using the Cauchy index, actually a lot of this is from complex analysis, and we're actually not going to need it. The next thing he does is simplify the Cauchy index to be this function, and then simplifies it further to just use v of a minus v of b, the Sturm sequence, giving one final equation for the number of roots inside of a rectangle of the complex plane. If you're wondering what those q values are, those are the 4 coordinates of your rectangle. I went ahead and used our same example of x cubed minus 1, drawing 3 rectangles, and using Wilf's equation, plugging it in to get 3 roots in our large red rectangle, 1 root in our smaller blue rectangle, and no roots in our smallest black rectangle. There are some considerations though to make this work, because we're applying a real number line test to the complex plane. What you have to do is expand p of x around whichever point you're looking at, q, and then do a substitution to replace x with this expression of q, giving you a new value of p which we'll call p bar, which involves complex numbers. Then how do you make your v function work when you have complex numbers? Well, we have a new starting f for our v sequence. Our f0 is just the real part of p bar, and f1 is what was in the imaginary part, ignoring the actual I. Then the rest of our Sturm sequence is the same with the remainder division, meaning the only inputs into our v function are 0 and the distance between q sub k plus 1 and q, meaning all of our numbers are real. You don't actually have to make v work with complex numbers. And so Wilf was able to apply Sturm sequence and generalize them to the complex plane. I will note, though, that he calls this method global bisection, and bisection implies that you're just dividing something into 2 sections. With 4 sections, the method should really be called quadrisection. Quick reminder, root finding is hard. The Lehmer-Schur algorithm, although elegant, wasted a lot of search using circles. The solution is to use squares. Sturm sequences are useful for finding the number of real roots in an interval as an extension of the Fourier theorem, which we then generalized to the complex plane by Wilf and others, giving us quadrisection. It finds all of your roots, even if they're complex, even if there's multiplicity, guaranteed in a linear order, and also parallelizable. As always, thank you for watching. I'll go ahead and post the code for this on GitHub. And if you like this video, definitely check out my other topics on Lehmer-Schur and Jenkins-Traub.